So today we will learn valid and invalid arguments, inference rules and deductions. Firstly, we need to understand what are arguments. An argument, it consists of a list of premises followed by a conclusion. Written as P1, P2, P, similarly it goes on till Pn and a conclusion. So this is an argument which consists of the premises followed by a conclusion. Now the argument can be valid or invalid. So we have two types of arguments, valid and invalid. Now when is an argument said to be valid? An argument is valid whenever all premises are true, the conclusion is also true. And an argument is invalid when all premises are true but the conclusion is false. Suppose it is given to us that P implies Q, P, therefore Q. This is the argument given to us where this is P1, that is the first premise, and this is P2, which is the second premise, and this is the conclusion. We need to find out whether this argument is valid or invalid. So how can we do this? We can construct a truth table, PQ. What are the possible values of P and Q? True together, false together, TF, FT. P implies Q. True. Here we give it the benefit of doubt. Here P is true but Q is false. So P implies Q is false. And here again we give it the benefit of doubt. So it is true again. So what is P1? This. And what is P2? This. And what is the conclusion? This. So an argument is valid if when all the premises are true, then the conclusion is also true. Here the premise 1 is true and so is the second one, and the conclusion is also true. Thus we get that the argument is valid, because whenever the premises are true, the conclusion is also true, and hence the argument is valid. Now let us present an example of an invalid argument. Suppose it is given to us that P1 is P or Q and P2 is Q, and the conclusion is P. Again we can check the validity of this argument by drawing the truth table. True together, false together, TF, FT. What is P or Q? P or Q is true. Both of them are false, so it's false. One is true and another one is also true. Now again, what is P1? This one. This is our P1 and this is our P2 and this is our conclusion. We find that whenever the premises are true, the conclusion is also true. Thus, because of this, we can say that the argument is valid. But again, look at the fourth case. When the premises are true, the conclusion is false. This one. So whenever we come across such a situation that whenever the premises are true, the conclusion is false in that case, then we say that the argument is invalid. In this case, the T and T does not matter to us because we have a T and F. So this is supposed to be ignored. What we are concerned about is just the fourth case, where whenever the premises are true, the conclusion is false, and we can say that the argument is invalid. Now we are done with the valid and invalid arguments. Now let us move to inference rules. Now what is an inference rule? An inference rule is a valid argument that can be used for deriving deductions. So what are the important inference rules? The first one is Modus Ponens. What does Modus Ponens say? P implies Q and P, therefore Q. This can be proved with the help of a truth table. It is constructed. We just did this one before. We proved that it is a valid argument in the previous example for proving a valid argument. So we can prove modus ponens with the help of a truth table as done already. Now what is the second inference rule? Modus Tollens. What does Modus Tollens say? P implies Q, negation of Q implies, therefore, negation of P. Now this can be proved again with the help of a truth table. We can prove that this is a valid argument. P, Q, P implies Q, negation of Q, negation of P. True together, false together, T, F, F, T. P implies Q will be true, true, false, true. Negation of Q will just reverse the signs. Similarly for negation of P. Now we must prove that this is a valid argument to show that it is an inference rule. So whenever the premises are true, the conclusion should also be true. We check it. Here we have a T, T and F. And we also note that we do not have any T, T and F. We only have a T, T and T. If we had had a T, T and F, then the valid would have been invalid. So we see that this argument is valid, and thus we can prove modus tollens. Now, what is the third inference rule? Third inference rule is disjunctive addition. What does disjunctive addition say? P, therefore P or Q. Now this is quite logical. What does P or Q state? P or Q basically means that either P is true or Q is true, or both of them are true. So it is obviously given to us that P is true because P is a premise. So obviously P or Q is also true. But again we can prove this with the help of a truth table. P, Q, P or Q, T, 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 F, F, T, F, F, T. P or Q will be true, false, true, true. Now this again is P1 and this is the conclusion. So we see, because of the first one, it is a valid argument. We don't have a condition where P is true but P or Q is false. Thus we cannot say that the argument is invalid. And hence we prove that this argument is also valid, and disjunctive addition is thus an inference rule. What is the next inference rule? Conjunctive simplification. What does this inference rule state? It states that P and Q, therefore P. This is again quite logical because P and Q means that P is true and Q is also true. So obviously we can state P. This can also be written as, conjunctive simplification can also be written as P and Q, therefore Q. Right? Because P and Q basically means that P and Q, both of them are true. Now what is the fifth inference rule? The fifth inference rule is disjunctive syllogism. What does that state? P or Q, negation of P, therefore Q. So this is again logical. P or Q means that either P is true or Q is true, or both P and Q are true. But in the second premise we are stating that P is false. Thus it is quite obvious that P or Q is true only if Q is true, because P is obviously given to us, it is false. This can again be proved with the help of a truth table, with the headings being these. And this is P1, this is P2, and this is our conclusion. We will find that whenever these two are true, this is also true, and thus we can state that this is a valid argument. Now, what is the sixth inference rule? The sixth inference rule is conjunctive addition. What does that state? P, Q, therefore P and Q. This is again quite logical because it's given to us that P is true, Q is true. So obviously P and Q is supposed to be true. We can prove this as well with the help of a truth table. Now, what is the seventh inference rule? It is hypothetical syllogism. What does that state? Hypothetical syllogism states that if P implies Q and Q implies R, then P implies R. Let us prove this with the help of a truth table. P, Q, R, this is going to be a long one. True together, false together, T, F, F, T. We will just rewrite this. True together, false together, T, F, F, T. And for these, for the first four, we will assign R a truth value, and for the last four, we will assign it a false value. Now what is P implies Q? True, true, false, and again true. Again it's the same, true, true, false, true. What is Q implies R? That is these two. True, 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 false, true, true, and again a false. What is P implies R? That is these two. It's true, 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 false, true, false, and true. So in this case, this is our P1, this is our P2, and this is the conclusion. What do we find? T, T, T. Is there any TTF? TTF? No, there is no TTF, but we have 4 TTTs. So we can say that this argument is valid, and thus we have proved hypothetical syllogism as well. So these are the 7 inference rules that can be used for deductions. Now firstly we will, before moving to deductions, we'll do certain errors. Errors that commonly occur, which must be avoided. So the first error is called Converse Error. What does the Converse Error state? The Converse Error states that P implies Q, Q, therefore P. Now this is an invalid argument. What is valid is that P implies Q, P therefore Q. Suppose, let us present an example here. Suppose it is given to us that P1 is, suppose P1 is x is greater than equal to 2, then x is greater than equal to 0, and P2 is x is greater than equal to 0. And we are just saying that therefore x is greater than equal to 2. This is obviously quite invalid because what is the first premise? X is greater than equal to 2. That is x is 2, 3, 4 to infinity. Right? And this obviously implies that x is greater than equal to 0. The second premise is that it is true that x is greater than equal to 0. And we are concluding that therefore x is greater than equal to 2. Which is obviously false because it might happen that if x is equal to 1, in that case, this premise is satisfied, it is greater than equal to 0, but it is certainly not greater than or equal to 2, right? Had this been x is greater than equal to 2, then our argument would have been very much valid, and this had been 0, then this argument would have been very much valid. We can still prove this with the help of a truth table. Let us proceed with it. PQ, P implies Q. So these are true together, false together, TF, FT. P implies Q is true, true, false, true. What is P1? This is P1, this is P2, and this is C. Right? So we find that there is a TTT, but there is also a TTF, which makes the argument invalid, and thus we have proved that this is a converse error. What is the second type of error that we must learn? It is the inverse error. What does the inverse error state? P implies Q, negation of P, therefore negation of Q. Let us consider an example for this. Suppose P1 is x is greater than equal to 2 implies x is greater than equal to 0, which is obviously true. And P2 is x is not greater than equal to 2. And we are concluding that x is not greater than equal to 0. This argument is obviously invalid because the first one states that x greater than equal to 2 implies x greater than equal to 0. Second one states that it is not the case that x is greater than equal to 2. Thus, x is not greater than equal to 0. But what if again x is equal to 1? In that case, this is satisfied, but again this is not satisfied because x equal to 1 is certainly greater than 0, right? So now had this been 0 and this been true, 2, then the argument would have been very much valid. So again, let us prove the inverse error. PQ, P implies Q, negation of P, negation of Q. True, false, T, F, F, T. This is true, true, false, true. This is false, true, false, true, and this is false, true, true, false. What is P1? This. What is P2? And this is the conclusion. We find this, which makes the argument invalid, and thus we have proved that this is an error since it makes the argument invalid. So these are the two errors that always must be avoided. Now we move on to certain deductions where we will make use of the inference rules that we have just learnt. Suppose it is given to us, given a list of premises and a conclusion. So this is an argument and we must prove that this is, and we must derive this conclusion from these premises. So what are we doing here? We are doing deductions where we will be using the premises to derive a conclusion. So how will we be proceeding with this? So the solution to this is, we firstly need to thoroughly learn all the inference rules, right? So firstly we'll be considering these two statements. What do we see here? Which inference rule can be used in P3 and P4? Modus Tollens, right? So what do we write? What is the first step in our solution? It is negation of P. And how do we get it? We write that in the bracket. P4, P3 and Modus Tollens, right? Because P implies T, negation of T, therefore negation of P. This is what Modus Tollens state. Now, what can we do next? Next, this is a very important step. We can now use disjunctive addition here. Where can we use disjunctive addition? You see, not P or Q implies R and we have not P. How about we use disjunctive addition here and write this not P or Q, right? So what are we basically using? We are making use of the first step and disjunctive addition. This is the second step. For the third step, we will now consider these two statements. We have proved, it is given to us that not P or Q implies R and not P or Q is true is what we have derived from not P. Here we can make use of Modus Ponens and arrive at R. How? Making use of P1, step 2 and Modus Ponens, right? This implies this is true, therefore R is also true. Okay? Now, in the fourth step, what can we do? You see, negation of P is true, R is also true since we have derived these. So what can we do? We can write this as not P and R using step 1, step 3 and which inference rule is that? Yes, this is conjunctive addition. So using conjunctive addition, we have got not P and R. In the fifth step, we will again make use of Modus Ponens. It is given to us that not P and R implies not S. Not P and R is true since we have proved it here. So we can make use of P5, step 4 and Modus Ponens and arrive at negation of S, right? Now, what can we do next? We need negation of Q. So, you see, we can make use of P2 and step 5 and we can use which inference rule here? Disjunctive syllogism. By disjunctive syllogism and this P2 and this step 5, you see S or not Q, negation of S, then obviously negation of Q must be true and thus we derive the conclusion and our deduction of this conclusion is complete. Let us consider another example. Suppose it is a sentence is given to us. Suppose this is given to us. If it rains, we will not have a picnic. If we do not have a picnic, we will not need fruits. Therefore, if it rains, we won't need fruits. So, we see here that this is P1, this is P2 and this is the conclusion. So how can we write it in the form of premises and a conclusion? Firstly, let R denote it rains. Let P denote we have picnic, and let F denote we need fruits. How can we build the argument here? P1 is, if it rains, then we will not have a picnic, right? What is P2 here? If we do not have a picnic, we will not need fruits. Therefore, if it rains, we will not need fruits. Is this argument valid? Yes, it is very much valid. By which law? By which inference rule? Hypothetical syllogism. So we can also have the premises in the form of sentences, which we will have to write in the form of symbols. Suppose this is an example. P and Q implies R. P and Q implies not P or not Q. R implies S. Q and not S. Therefore not P. So this is an argument given to us. So what are the steps that we will proceed with to deduce not P? Now, how can this problem be solved? What is the first step? From P4 and from P4 we can get negation of S by conjunctive simplification, right? Q and not S implies Q is true and so is negation of S, right? So negation of S is true, and by conjunctive simplification we arrived at negation of S. Now we can use Modus Tollens here and get negation of R by using step 1, P4 and Modus Tollens. You see, Q and not S, R implies, this will be P3, R implies S, negation of S, therefore negation of R. Now, what is the third step? In the third step, we get negation of P and Q. How are we getting this? We are making use of step 2, P1 and Modus Tollens, right? P and Q implies R, negation of R, therefore negation of P and Q. Now we can apply the De Morgan's law here and get negation of P or negation of R, right? Now, what else can we do here? You see, we also get Q from P4 and conjunctive simplification, right? We use conjunctive simplification here and get Q. So the fifth step, in the fifth step we will make use of step 3 and step 4 and disjunctive syllogism, right? Not P or not Q and Q. Now what is Q? Q is basically double negation of Q, right? So this is indirectly this, right? By disjunctive syllogism we are getting negation of P when we are using these two steps by disjunctive syllogism, and thus we have proved our conclusion and we have deduced it. With this we come to an end of our video. If you have any doubts, then you can write them to me in the comment box. Thank you.